Good afternoon, everyone. Welcome to our final presentation. Thank you so much for coming today to see our presentation. We are really excited to present our project, the Remotely Piloted Aircraft Systems Imaging System Upgrade for UAARG. My name is Imtisal Ahmad, and on our team we have Ricky Au, Andrew Dearborn, and Ryan Sandoval. A little bit background information before we get started. The University of Alberta Aerial Robotics Group, UAARG, is our client. UAARG is a student club that participates in competitions involving machine vision related tasks. So for this year's competition, they're presented with a scenario where they must defend an embassy from malicious entities. One of the tasks involves tracking a suspicious person and providing identifiable characteristics, as well as providing a video stream to judges. The current imaging system is no longer sufficient to accomplish these tasks because it can only take photos. Therefore, we need to upgrade the hardware and the software to produce a video stream to track the intruders. Our project aims to perform this upgrade while retaining the pre-existing features in the old system. So our prototype has end-to-end data transmission between the camera and the ground station. This will enable the ground operators to capture videos and images from a remotely piloted aerial system and stream data to the ground from multiple cameras, as well as having the ability to control camera properties such as brightness, contrast, and hue, and having access to custom image processing, which will further help them find a human during the course of the competition. So now our group will like to give you a demo of our imaging system upgrade.
Alright, first we will begin with a quick overview of our hardware components. This is the Odroid. It is a single-board computer that runs the entire system. It is connected to the camera array, currently consisting of 2 cameras. These cameras are capable of both video and image capture. The reason that there are 2 is because we want to be able to switch perspectives mid-flight. So for example, if one camera was able to see, let's say in front of the plane, then if a target currently in view were to move down out of line of sight, we could switch to a second perspective that could continue to track the target without having to make a second pass with the aircraft. That is it for components that we have created. Next, we have the client-provided components. These components can include an antenna that it connects to a router, which has its own transceiver, and both of these connect to our stand-in for a ground station, which will be controlling the Odroid with our demo software. Next, we have the drone itself. Once we open it up, you'll be able to see that the Odroid was specially selected so that it would just barely fit within the hull of the drone. Underneath, we can see one of the cameras securely attached to the bottom of the drone to show where one of these cameras may end up in the final version. Now we can begin with a demo. On the left, you will see our demo software, and on the right will be the folder where images will be received. To start off, we will do image capture as well as perspective shifting. The operator has commenced image capture, and as you can see, images as the folder is refreshed will be received, and clicking through them we can see they are from my right perspective. Now, on the other side, switching camera perspectives to camera 1, we can now restart image capture, and slowly, as new images come in, you will see images from my left perspective. Ideally, these images would be shown in a 1 frame per second slideshow. Unfortunately, this was not part of our requirements, so we did not have time to fully implement it. Next, we will demo some of the features that we have surfaced from our API. Here, it seems that the camera is already observing a suspicious person within the laboratory. Now, if hypothetically this were a very bright sunny day, perhaps the operator would want to reduce the brightness of an image to improve clarity. The operator in this instance has reduced the brightness of the image to its lowest point, and unfortunately this is not very helpful in a moderately lit laboratory. Now the operator will return the brightness to a reasonable level and will activate the edge detection options edge detection could prove very helpful later on when machine learning applications are further explored. There are more of these kinds of options in our API that will be available to future developers. However, they are not surfaced in this demo program. Lastly, we will cover the streaming functionality, as well as a pseudo-practical situation for perspective switching. Here we have the live stream feed on the right side of our screen. We observe a suspicious person making their way across our perspective, but we lose sight of them. So the operator must switch cameras in order to try and find this person again. Fortunately, this switch in perspective allows the operator to observe their target for a little while longer.
Now a little bit about the design process itself. I'm going to start off with the positive. As demonstrated in our demo, we have a successfully performing prototype. Starting with assembling the entire system, this consists of the hardware setup, so the board and the cameras, setting up a VPN for the rest of the group members to have remote access to the board, and creating a build environment using Meson. This part was fairly simple. We were able to achieve our key functional requirements of having image capture and video capture on multiple cameras. We were able to stream videos on both cameras as shown in our demo, as well as enabling camera controls that enable the imaging operator to change camera properties such as brightness, contrast, and hue. Our system also contains a dynamically customizable image processing pipeline, which allows the images to get pre-processed as per the competition requirements. For example, enabling edge detection to find humans during the course of the competition. This would really help the imaging team locate malicious entities during the competition. However, this can always be customized to meet competition requirements in the future.
Thanks, Imtisal. I'm Sandoval, and I'll be talking about what didn't go well in the project. So, despite the successful implementation of the prototype, there were some challenges encountered during the development that remains to be fixed. The issues are present in both hardware and software. On the hardware side, the insufficient USB bandwidth of the system created corrupted images and occasionally prevented any images or video captures from happening. Here's an example of this issue occurring. We can see that the output is just a gray screen. During development, we narrowed down this issue to insufficient bandwidth for the USB 2.0 ports. In our case, since our cameras are using USB 2.0, they were not able to use the bandwidth available to the USB 3.0 ports on the Odroid XU4. This limited our bandwidth to a maximum of 480 megabits per second, which must be shared between the two cameras. Note that we don't expect this issue in USB 3.0 ports since they generally have a bandwidth of 5 gigabits per second. A quick calculation can showcase this issue. Given that we have an 8 megapixel camera with 24-bit color depth, and assuming a capture rate of 1 frame per second, a single camera needs 192 megabits per second of bandwidth. With two cameras, this is doubled and we have 384 megabits per second of bandwidth needed. If we assume a 80% utilization of USB 2.0's theoretical 480 megabit per second bandwidth, we can see that the bandwidth needed and the available bandwidth are the same. This calculation is a simplification of the data transfer rate, but it's evident that the system does not have enough bandwidth to create high-resolution videos that conform to the specifications. On the software side, the stream latency was a significant issue. Early on in the project, objects that enter the view of the camera take approximately 10 seconds to show up on the ground station stream. Through fine-tuning in the FFmpeg configurations, the stream latency was reduced to 2 to 3 seconds. However, this latency is still quite large because fixed-wing drones travel many meters per second, and the extra seconds lost can delay flight maneuvers that the drone has to perform to track subjects of interest. I will now pass it on to Ricky, who will be talking about the future work for this project.
We have 4 potential improvements. The first is utilizing a second board that is more powerful than the Odroid we used for the prototype, As we have seen in the What Did Not Work section, we ran into issues with video streaming due to not having enough bandwidth. This second board would have a stronger processor to have more available bandwidth and also allow for more cameras to be added to our camera array, since currently our prototype can only support 2 cameras at a time. Secondly, we could use machine learning to implement software that will automatically crop out parts of the image that does not contain the person of interest. This improvement would also reduce the overhead on the communication systems, as well as increase the throughput of useful information to the ground station. Third, we can reduce the power draw of the system to maintain maximum flight time. One way to accomplish this would be to implement a sleep function on the second board so that it is put to sleep whenever the camera array isn't required. Lastly, in order to make the prototype function for the demo, we needed to cut out the Qt library that was utilized in the old system. So this means future work will be needed to connect our prototype API to the plane's main system. In conclusion, we developed a system that captures video on a remotely piloted aircraft system and transmits this stream to a ground station for processing. This concludes our presentation on the RPAS imaging systems upgrade. Feel free to ask us if you have any questions. Thank you.